interface between the regions. And most of the talk I'm going to be referring to, actually all of the talk I'm going to be referring to three-dimensional Chern-Simons theories. And in that case, this sort of physics is very familiar, because if you take a Chern-Simons theory and cut it open, what you find is a Wessel-Witten theory on the edge. Okay, and in fact, the non-factorizability of the Hilbert space is manifest. Now let me just set up some way of thinking that I'm going to use throughout the talk. Okay, so we're going to think about Chern-Simons theories on a space-time 3 manifold. Okay, and locally you can think about that as just time across a surface. Okay, and normally we would construct a state using a path integral over a half space-time. Right? You would integrate from t equals minus infinity to some fixed time, call it t equals 0. And a nice way to, because this theory is topological, a nice way to think about that half space-time is to take the interior, to take it to be the interior of some Riemann surface. Okay, so if sigma is a Riemann surface, then the half space-time that defines a state is the solid, is just, fill it in. And you can think about time as sort of the radial direction inside, say, the torus, if you want to consider that case. Okay, that's a very basic construction, and what it does then is it associates the Hilbert space to each Riemann surface. Okay, and the various states in that Hilbert space are given by looking at non-trivial Wilson loops in that space-time. Okay, so an example of this non-factorizability is for example, if you take space to be a two-sphere, okay, then you can think about cutting that in half, cutting the sphere into two disks glued along their edges. Now, for the sphere, the dimension of the Hilbert space is just 1, and the reason is that there are no non-trivial Wilson loops that you can draw on the sphere. Okay, they're all contractible. But on the disk, because it has a boundary, the Hilbert space is given by the Wessel-Witten theory, and certainly that, depending on the details of the Chern-Simons theory, it certainly has a large Hilbert space. Okay, so you don't get, so it's just not true that even though when you take the union of these two spatial regions, you don't get that the Hilbert spaces are just the product. In fact, it's a very small subset of the Hilbert space of the product. Okay, so nevertheless, the bottom line is that it's complicated to talk about entanglement entropy in gauge theories, but nevertheless, this bipartite entanglement is well understood, and this is something that we worked on many years ago. The general form of the entanglement entropy, in particular when you compute it, is that there's the so-called area law. And so if I was to take the Chern-Simons theory and regulate it in some way, introduce a cutoff, then invariably you would find as the leading effect such a divergent area law term. Okay, but in addition, so that's non-universal. It doesn't mean anything because you can change the cutoff and change the value of that. But what one finds is that there's a finite contribution, which is universal. And in fact, the calculations that we did there were based on formal surgery methods that Witten had developed back in the 90s, and the replica trick. And what one sees when one does those calculations is simply the topological part of it. Okay, you're not, because you're doing formal surgery, you don't see any power law divergences. Okay, but in fact, it's a rather complicated story because this topological entanglement depends on many details. Okay, for example, it depends on some simple data of the CFT that's dual to the Chern-Simons theory. For example, modular S matrix. That's something that we'll see again later on. But it also depends on, so in the case where the Hilbert space of the spatial slice is multidimensional, one has to choose a state in order to construct the density matrix, and the details depend on that choice of state. And it also depends on precisely how you cut the Riemann surface. Okay, so that's, I'm not going to review that. What I'm interested in, so just backing up there, what I was talking about here was taking space to be a single Riemann surface and defining a reduced density matrix by chopping that in pieces in some way. Okay, and so that's what I was saying here. In the present case, we're interested in something different, which we're going to refer to as a multi-boundary or multi-partite entanglement. And the basic idea is that you can take three geometries that have multi-component boundaries. Okay? So, for example, you know, this is just a cartoon again, but you could imagine that space is just a disjoint union of surfaces. And what that will give you is a Hilbert space, which you can think of as just a tensor product of the Hilbert spaces associated with each one of those Riemann surfaces. Okay. So we're gonna study this in quantum field theory, in particular in topological quantum field theories. But a similar sort of thing was studied recently in the last few years in the context of ADS3 CFT2. So they were talking about multi-partite entanglement in two-dimensional CFTs, and their method of attack was to use the RT formula in ADS3. Okay, so what I'm going to talk about is three-dimensional Chern-Simons theory. Hopefully you're familiar with the action of that. Integrated, it's topological, it doesn't involve the introduction of a metric. It's integrated over some choice of three-manifold, and there's a level called K in front of the action. And we're going to look at this in the case where the gauge group is either U1 or SU2 for simplicity. And I'll talk about some generalizations of that at the end of the talk. Okay, so again, so what we're going to do is we're going to, you can imagine, heuristically at least, doing a path integral over some three-manifold with some number of boundaries. Okay, so I'm going to, as I've been saying, we're going to think about the full boundary as a union of several pieces. Okay, and what one does to get a wave functional is you just do the, as we said, we do the path integral over that half space with some specified boundary conditions at each component of the boundary. Okay. So, crucial to this construction is the following. So this is probably the most important slide in the talk. The question is, the basic question is how can we generate three manifolds that have multi-component boundaries? Okay, and so here's the construction that we employed. Okay, so if you start with a closed three manifold, and we're always going to talk about a three-sphere here. Okay, and you consider an n-component link. Okay, so you can think of this as a mapping from n circles embedded into the three manifold. And in general, of course, those things will be linked and knotted in complicated ways. Okay, so I'm going to think about, so the notation I'm going to use is that my n-component link you can just think of as a union of the independent curves. Okay, and the construction is to take that picture and to fatten the components of the link. In other words, we take a tubular neighborhood around that, around each of the components. Okay, so that's denoted here. And so each one of these now is a torus. Right? So you have tori that are linked. And as long as the neighborhood is sufficiently small, then you can think about those tori as linked, but not intersecting. Okay? So we're imagining that they're separate from each other. And the complement of that fattened link then is a 3-manifold with an n-component boundary. Okay, so it's given by that. Now, if I do the Chern-Simons path integral on that link complement, okay, it's a 3-manifold with boundary. So what I'm going to do is I'm going to generate a state. I'll call that state the ket Ln. Okay, and as I said, you can think about that as living in the tensor product of the torus Hilbert space, one for each of the components of the link. Okay, so let me, before I go on, let me back up and understand a little bit about the Hilbert space on a 2 torus. Okay, and as I briefly said a few moments ago, you can think about that as related to Wilson loops, and the way that that comes about is as follows. Okay, so I'm taking space to be a torus. Okay, and there's a basis of cycles on that torus, the A and B cycles. Okay, and as we were saying, we're going to think about space-time as filling in that torus, taking the solid torus. And in that space-time, then, the cycle that I'm calling M here is contractible. Right? I can shrink it to nothing, but L is non-contractible, and it can support a Wilson loop on. Okay, so what I have to do then, if I do the integral over this solid torus, the various possibilities are obtained by putting Wilson loops in a given representation on that cycle L. Okay, and that defines a state that I'm going to call J. Okay, and the dual state is associated then with the dual representation, and there's some orthogonality condition. Okay, and these representations refer to these are the integrable representations. Okay, so in fact for U1 or SU2, there are a finite number of these, which is determined by the level. Okay, so for example, so these are actually, you can think about these things from the point of view of the dual CFT. Okay, so these are the representations that I'm talking about here are collections of Virasoro modules from that point of view that have a definite SU2 charge, and they form. And what's going on is that they form into modules of the affine SU2. And as I said, there are a finite number of those. The J label on the lowest weight states runs from 0 to k over 2 in the case of SU2. And in the case of U1, there's a charge. There's a U1 charge Q that runs over k values. Okay, so it's in this sense that the Hilbert spaces are finite dimensional. Okay. And corresponding to that, I'm taking here simple enough Chern-Simons theories that the dual conformal field theories are rational, and this is one of the reasons that they're finite dimensional.
Well, how does this, just to make sure I understand, how is this torus related to the picture you had on the previous slide?
So this is one of the spatial tori. Okay, so you should think about this as n tori.
Yes.
Okay, and the 3-manifold is the complement of the tori that I've drawn there. Right? So if you like, locally around say one of these things, you can think about a chunk of space-time as being a solid torus.
Yes. Okay. So here the space-time is a complement of the solid torus, and then the next
Yes.
slide it's the solid.
That's right. That's right. So
they're the same.
they're the same. One way to think about that is that if you a simpler case is that you can generate a 3-sphere by taking a solid torus and gluing it to another solid torus. And what you have to do is you have to do an tau goes to -1 over tau when you do the gluing, and that topologically is a 3-sphere. That's right. So the interior of a torus and the exterior of the torus are essentially the same thing.
So I'm sorry. Here you cut out these links, and then to get the total space, you are gluing 2 copies of the complement.
No.
No.
So what this picture is this is a picture of a 3-manifold with n component boundaries. That's it.
Yes. Okay.
So I do the path integral on the
right.
complement of the one.
In the other case, you're doing a three manifold
Okay.
with just a single torus.
That's right, so I'm thinking, so what I'm doing is, so what I said was is that we're gonna think about this as living in the tensor product. So let's first understand the Hilbert space on T2. Now, unfortunately, the discussion was that when I was talking about this, I was saying fill it in.
Right.
Okay. But you could also fill the outside.
No.
And it's equivalent.
But if you have these others, you cannot shrink this M cycle anymore, or not?
Right, that's what.
That's right. That's right.
So this won't carry over verbatim to those other Hilbert.
Well,
The-
let
okay.
me finish telling you what the state
Sure.
is,
Mhm.
and then, but the point is that you get a state that lives in the tensor product.
Mhm.
Okay? But it's not a trivial state, and that's kind of the point. I mean,
Okay.
it's
I
gonna
think
be-
you're saying it doesn't matter how you get the states. Once you have the states on the surface, you have them. So once something comes from the inside, or you can get them from the outside. We just want to know what they are.
Right.
I don't quite understand that. I thought the states are a property not of the surface, but of the three manifold. And the
Another way to
third.
say what I'm doing here is I'm just telling you what a convenient basis is. Okay, so the arbitrary link complement state lives in the tensor product of T2 Hilbert spaces. Okay, and I'm not telling you anything about a state at this point. What I'm doing is I'm telling you what a basis element.
Okay.
And these are the basis elements.
And also, maybe both are not contractible or not in their case.
Sorry, I didn't, what?
Is
No,
the
I
M
don't-
cycle
I'm not-
generally contractible now in the, on the previous slide?
No,
No.
no. No, absolutely not.
So
But-
L and M are not contractible if you have another torus or not.
If it's linked.
So you can throw them in
But
without-
again, let me
Okay,
finish telling
okay,
you what
yeah.
what the states are, and then we can discuss. Okay, so the point was that, okay, so think about that as the basis element for a given component. Okay, so the claim is that given a link and the complement, what I can do is I can express that as a linear combination of basis states in the tensor product. Okay, so there's a wave function, if you like. There's the coefficients. Okay, and what are those? Well, it turns out that they're just the expectation values of the product of Wilson lines, one Wilson line on each component of the link. Okay. Why is that? Well, if I was to take this formula and contract it with J1, J2, Jn, because these guys are orthonormal, it just isolates one of these terms. Okay, so this wave function is the overlap in the link state with the corresponding basis element. Okay, and that is the point is that is the Chern-Simons path integral with specified Wilson loops present. Okay, so this is the claim. So these things are called colored link invariants.
Okay.
And I'm waiting for
So, so why aren't there Wilson loops in this geometry that wrap what you were calling the M cycles of the individual links before? Those are not contractible cycles in general.
Right. So,
anymore.
but you can pull them off, and I think you can. Actually, I haven't shown this in detail, but the idea is that for something that wraps this way, you can pull it off and understand that it
maybe it becomes another
includes-
J.
It becomes
Because,
another J.
Another J.
Yeah, that's it. Okay.
Okay.
All right, so if we knew what all of these things were, then we'd have a lot of information about states in material. Okay. So what I'm going to do is I'm going to construct various entanglement measures given these states, right? Remember the basic idea was that of spatial entanglement was that you would construct a reduced density matrix by tracing over some subset of the space. And here I'm going to do something very simple, which is I'm just going to partition the link into the union of two sets. Okay, where the union is, so I'm talking about the total Riemann surfaces, right? In other words, I'm not slicing up the Riemann surfaces now as we did in the one component case previously. I'm just taking subsets. Okay, and so what I'm going to do is I'm going to construct a reduced density matrix by just tracing over, say, the red ones in the picture. Okay, what does that mean? It means tracing over. I can do that in this basis that I construct. Okay, so why is this an interesting thing to do? Well, there's sort of an old idea, a vague old idea, that quantum entanglement might be related to topological entanglement in some way. Okay, and so what we're doing is we're testing that idea in a playground where you can do explicit calculations. Okay, and so in the rest of the talk, what I'm going to do is sort of build up some, by looking at various cases, I'm going to build up some intuition for how this actually works. Okay, the simplest thing that you can say is that if you take the link to be the unlink, okay, so if you just take, this is maybe the case where you're most happy with, right, because now you don't have the components of the link linked at all. Okay, well, if you buy what I said and you compute the expectation value of Wilson loops on this, it's known that factorizes into a product of the Wilson loop expectation values on each of the loops. Okay, what that corresponds, in my language, to the statement that the state corresponding to this unlink is a product state. Okay, it just factorizes into pieces. Okay, and so consequently, if you were to calculate entanglement entropies of this state, you would just find that they all vanish. Okay, so in that sense, you can expect that there's some properties of the linking of these components that have to do with the quantum entanglement. Okay, and what I'm going to see by looking at various cases is that in some cases, the entanglement entropy doesn't even depend on how knotty a component is, and in some cases it does.
So, I'm a little confused about something. So normally in ADS-50, if we start with the boundary and define these entanglement measures in the boundary, we wouldn't assume ahead of time we know what the 3D ambient space is. It would just be whatever the dominant saddle point is, we sum over different saddle points. In this case, it seems like you're assuming ahead of time that you know what the...
I'm not doing ADS-CFT, I'm doing field theory.
Okay.
And I'm telling you what my field theory is. It's a Chern-Simons theory.
Okay, so this isn't in relation to this. Okay.
Well, I'm not talking about ADS-CFT.
Okay.
But as you probably know, I mean, Chern-Simons
Sure, yeah.
is sort of holographic in a topological sense.
Right. This would be like one of the possible saddle points that you would sum over in the boundary theory.
I'm giving you a state. I'm not telling you what its weight is in some
okay.
some bigger
Right.
bigger picture. Okay. Another interesting feature of this, which I think is very important, is that the entanglement entropy that I just discussed, and we're going to construct in detail in the rest of the talk. Well, first of all, it's a topological invariant. Okay. Okay, so you can think about this as, you know, related to, say, Jones polynomials or something in specific cases. But importantly, there's another technical property that it possesses, which is that it's framing independent. And many of the topological invariants or not invariants that people talk about don't have that property. And this sort of comes in a sort of interesting way. Okay, so what do I mean by framing? Well, there's a technical thing that I'm not going to get into detail on, but when one defines that colored link invariant, that Wilson loop expectation value, there's a technical requirement that there's a choice that you have to make when you choose an L cycle. Okay? You can think about this as you have to sort of fatten the cycle. Okay, and it turns out that different choices of that framing correspond to a unitary transformation on the states that we've just constructed. Okay, and because it's unitary, it doesn't affect the entanglement properties. Okay, so again, so in other words, the entanglement entropy constructed in this way is independent of the framing. Okay, so let's do the simplest possible thing, the abelian case. I'm just taking the gauge group to be U1, the level to be K. And the nice thing about this is that Witten calculated all of these states, or he calculated the data necessary to determine all of these states a long time ago. Okay, they're known in closed form. Okay, and translating that information into my language gives you this. The link state is determined entirely by what's called the Gauss linking number, and that's sort of the obvious thing, right? If I have two loops that are linked, this is linking number 1. If it went around twice, it would be linking number 2, etc. Okay, so I call that Lij. Okay, and good. So the state is just given by this. Okay, again, remember that in the case of U1, the representations were determined by a charge Q that went from 0 to K minus 1. It goes over K values. And I've used this framing independence to restrict the sum to be I less than J. In other words, there's no self-linking. Okay, or if you introduce that, it would never contribute. Okay, so again, this is what I'm doing. I'm partitioning the set of components into two sets and tracing over one of them. Okay, so let's start with the simplest thing, where you have two components that are linked, so two loops, okay, called 1 and 2. Okay, the state then just depends on that linking number of those two components. Okay, and I construct, for example, a density matrix by tracing over the second guy. Okay, and so that gives me a density matrix in the 1 Hilbert space, and here are the matrix elements of that. They're just, it's a simple computation. You just get this sum. Okay. Now, what's in the sum are kth roots of unity, right? And so, you're summing over all values, so you're almost always going to get 0 from this sum, right? Because they add up to 0. The only exception is where this quantity here is 0 mod k. Okay, so what would I do? So that's my density matrix. I just told you all of the components of that matrix. What you can do to get the entanglement entropy, the simplest thing to do is to just diagonalize it, find all the eigenvalues, and just compute the sum of p log p. Okay? And when you do that, it turns out, well, when you look at the form of that matrix, its form, the important thing in this computation is that it depends on the greatest common divisor of k and L12. Okay? And the reason for that is that you can think about rho 1 as being sort of a tensor product of a G by G matrix with all 1s times a unit matrix. Okay? In other words, it's just a matrix that has unit matrices everywhere. Okay? And this quantity turns out to be the log of k divided by that greatest common divisor. Okay? The simplest two-component link is called the Hopf link. It's just the simplest thing. Okay? In that case, L12 is 1. So the greatest common divisor is 1, and you just get log k for the entanglement entropy. Okay? And so the Hopf link is maximally entangled. It has the biggest possible value of the entanglement entropy in the case of two-component links. And so you can think about this as analogous to a bell pair in quantum information. Okay, now that's a brute force calculation. Another way that you could do it is you could use the replica trick. And remember what that is that you construct rho 1, and you construct trace of rho 1 to the nth power, and you take the limit n goes to 1. Okay, and you get the same answer. In fact, it's instructive to do that in some cases, particularly in the SU2 case that I'll talk about. Okay, now, so that was the two-component case. If you generalize to n components, okay, what we're doing is we're partitioning into two sets again. Okay, and we're going to trace over, say, the second part of the set. And when you do the same calculation that we just described, it's a little bit more involved, but you get sort of a similar formula. It's the log of k to the m, right, where the m is the number of remaining components, divided by some factor that I'll call the kernel of G. And what G is it's a linking matrix. Okay, so it's the matrix that you would form out of the linking numbers from loops that are in the first set, 1, 2 through m, and the loops that are in the second set, m plus 1 through m. Okay, it turns out that's, so in the two-component case, we had a 1-by-1 matrix, right, which was just L1, 2, and this is the generalization. And what I mean by this kernel G here is it's just the number of solutions mod k of this matrix times a vector of zk elements equal to 0. Okay, so this is some, you can refer to these as some sort of Diophantine equations. We don't actually know how to solve these equations, okay, except in the one case that I've already studied. In the two-component case, the calculation was that this is in fact just the greatest common divisor. Okay, but in general, this is sort of an interesting, at least to people that are interested in these sorts of things, this is an interesting number theory problem. Okay, and so there's some interesting interplay between all of these subjects. Okay, one thing that you can say is that the entanglement entropy for this partition will, there should be n minus m, this for that partition will vanish only if G is, that matrix is 0 mod k. Okay, that sort of saturates the kernel in that case. Okay, so anyway, the bottom line is that in the abelian case, what this quantum entanglement construction detects is that it just detects the Gauss linking of the components, right? That's all it knows about. And in particular, if I had a very complicated knot linked with a very complicated knot, right, it doesn't see the knottiness. It just sees the linking of those components. Okay, so you should think about the abelian theory as not very powerful from the point of view of entanglement. Well, you can define it carefully by flattening a link on the plane and counting crossings. But just think about it. If this is linking number 1, this is linking number 0, etc.
Or maybe give linking number 2 to help them out, right?
Okay, so
It wraps twice. Yeah, it's a
Yeah,
solenoid
solenoid.
that wraps grabs twice.
So if I go around twice, and there's a negative one.
Yes.
Right?
Right.
Depends on orientation.
But that doesn't need any framing for that.
No.
No. Not to define that. Okay. So let's go on to SU2 and try to see what happens in that case. And the problem here is that in the abelian case we knew what all of the wave functions are, and so we could just do the calculations explicitly. They were still hard, but theoretically, but you can imagine doing them. In this case, we don't know what the states are in general, and so what I have to do is to just pick a link and work hard and figure out what the state is. There are systematic ways to do this, but there's no closed form general formula for every link. Okay, so for example, the hop link again is particularly simple. Okay, so now I have a basis element J1, J2. Okay, and the colored link invariant is given by what's called the modular S matrix, or the component of the modular S matrix. Okay, and here's what it is. Here's what it is for SU2, but we don't actually need to know that much detail. What this thing is it's the thing that implements tau goes to -1 over tau. Okay, and the important thing is, as we'll see in a second, is that that's a unitary matrix. Okay, so there's the state again. Now, if I say trace over the second loop to get a reduced density matrix, okay, and take the matrix elements in the first Hilbert space, then you can see what I'm going to get is a sum of products of the S's. Okay, and this is just the J1 prime component of S dagger S. Okay, so that because it's unitary, you just get that simple result. Okay, and so again, well, this is not a hard computation now, right? Because I have an explicit matrix, I can diagonalize it. It's kind of easy to diagonalize it. It's a diagonal matrix. And so you can just write down the entanglement entropy as log of k plus 1.
So you believe in a sum over J1 and J2 or only J2?
I do not mean a sum over J1. So
Right.
I thought I got rid of all the typos. Okay, so again, this is maximally entangled, right? Because remember, k plus 1 is the dimension of the Hilbert space on the torus, and that's as big as it could possibly be. Okay, let's do something more complicated. The so-called Whitehead link is drawn here. It's like you take a figure 8 and put a loop through it. Okay, and okay, here's where you need to know what the Gauss linking number actually is. But when you compute it for this guy, you get 0. Okay, again, it's because of orientation issues. Okay, so if I was to do the abelian case on this guy, I wouldn't see anything at all, right? Because the linking number is 0, and so the entanglement entropy is going to be 0. It's just a trivial state as far as the U1 theory is concerned. In the SU2 theory, that's not the case. You have to work hard. I'm not going to show you the details of that, but you can compute the state systematically, and you can compute the corresponding entanglement entropy, and you find it doesn't vanish. Here's a picture, which you can't see, but it's a picture of the entanglement entropy versus K. Okay, and it just sort of increases. And in order to do the calculation, it's facilitated by some sort of amazing formulas that come from knot theory.
Is it, say,
And-
reason why it oscillates?
Back and forth. Yeah, we
Yeah.
don't understand that. It looks like it's jumping back and forth
then
across
it
a
goes,
curve, right?
smaller as you go to larger K.
Yeah. Yeah, we don't understand that.
And that's close to log k or log k plus 1? Or that curve, I mean, it's presumably
I
below.
forget, actually.
Okay.
It's not, well, yeah, log k plus 1 would be up here somewhere, I guess. But yeah, you're right. It would be interesting to have drawn that versus that. Okay. Anyway, the conclusion is that entanglement computed in the SU2 theory has more information than the abelian case. And what that more information is exactly, we're not sure, but it's more.
What's the meaning of reducing the link component?
Okay, so remember what I'm doing is I'm constructing the state corresponding to this link, and then I'm tracing over. In this, because it has two components, what I'm doing is I'm tracing over
That's what
one of the links. So the sum over J2 is the top link case, for example. Okay, so that's what. Okay, here's another case. Okay, so let's take a knot, okay, which I'll call K1, and just link it with a loop. Okay, and it turns out that when you do this calculation in the SU2 theory, the entanglement entropy actually knows that this is a knot. Okay, and that comes about, well, okay, again, I'm not going to show you the details, But it's, when you do the computation, you get, you just compute p log p, and the eigenvalues here, so ck1 of j is the expectation value of the Wilson loop on that knot, okay, in the representation j. Okay, and again, S is a component of the modular S matrix. Okay, so the SU2 entanglement knows about the knottedness of that component of the link through that link invariant. Okay, let's go further. Let's talk about three-component links. The simplest version of that is where I just take a chain. Right? You can sort of think of these things as hops linked together in a chain. Okay, and this is interesting because it turns out that if I take this and I trace over any one of the links, okay, you get the same answer for the entanglement entropy. Right? So say I trace over the third one, or say, for simplicity, let me trace over the second and third one. Then I get a density matrix in the one Hilbert space, a reduced density matrix in the one Hilbert space, a computed entanglement entropy. It turns out to be determined, the eigenvalues are determined by the quantum dimensions of the representations. Okay, and sort of remarkably, it doesn't, the picture looks like it ought to depend on which link you trace over, but in fact it doesn't matter. Okay, you get the same answer. Okay, I'll come back to that point in a moment. In terms of quantum information, this state you can think of as so-called GHZ-like. Okay, and so what I'm referring to here is, and again I'll come back to this a little bit later, but I'm referring to a classification of distinct states that have distinct entanglement properties in the case where I have 3 qubits. Okay, and it turns out that in that case there are essentially 2 different types of states you can get. The first is this GHZ state, where if I trace over any of the qubits, okay, so for example, if I trace over the first slot, you get a state that's mixed, but it's unentangled. Okay, so the result gives you something trivial from the entanglement point of view. Okay, so the claim is that that case is like that. Okay. Now, okay, so as I said, when you trace over any of the components of that link, you get the same answer. But the reason that you get the same answer is that you get a result. You get a density matrix which has the same eigenvalues. Okay, but it turns out that those density matrices are diagonal in different bases. Okay, so in other words, I have to do a unitary transformation to diagonalize the matrix, and it's different depending on the cases. So one way to distinguish those reductions then is to compute instead the relative entropy. Okay, so relative entropy is a gadget that sort of measures the difference between density matrices. So I have a density matrix rho and sigma. It's defined in this way. And here what I can do is I can compute the relative entropy of the reduced density matrix for tracing over link 1, say, versus tracing over link 2. Okay? And what you find is an expression like this. And as I said, this turns out to be non-zero, okay, because of this factor here. This is the remnant of a different unitary transformation that you have to do to diagonalize the individual density matrices. Okay. All right. So that's a pretty generic statement. Relative entropies can be used as a basis-independent way to distinguish components if the entanglement entropy itself doesn't do so. Okay, here's another couple of examples of 3-component links. Okay, I don't remember what the name of this is. It's in somebody's classification. It's called 633, and this one is 632. This is often referred to as Bormian rings. If you stare at this, you can see that if I was to erase, say, this loop, then the two loops are unlinked. Right? Okay, whereas in this case, if I was to erase this guy, you get the hot link. Okay, so that's the difference. These are distinct guys. Okay, and so if you compute the entanglement entropies of this guy, you find again, it's a lot like the three chain. It's sort of GHZ-like. But you can distinguish it from the three chain that we talked about before by looking at relative entropies again. Okay, the Bormian rings, on the other hand, this again is a case where there's zero Gauss linking. Okay, so the abelian theory has nothing to say about this guy. And it turns out that this is a case that is W-like. So this is the other possibility in this 3-qubit classification. The typical way this is written is that this corresponds to a state of 3 qubits like this. And if I trace over any one of them, say again the first slot, I get something that's still entangled. Okay. And so this is actually a little bit counterintuitive, because I mentioned previously that there was a little bit of literature where people were saying that, well, quantum entanglement and topological entanglement ought to be related in some way. Okay, the surprise here is that, as I said, if you just threw away one of these links, the other two guys are unentangled. But in fact, when you do the entanglement computation, they're actually still entangled. Okay, so that's a little bit subtle. In those old papers, at least the ones I've looked at, of course they didn't have any notion of entanglement like this. They didn't have this story, but they were, in fact, were talking about erasing components of the links and trying to say that this was trivial because of this. So they would have said, in fact, that this was GHZ-like. The entanglement says otherwise. Okay, so let me just, I'm doing remarkably well on time. Let me just finish up. Okay, so I think this idea that quantum entanglement and topological entanglement is pretty enticing. And so what we're doing here is we're just realizing this idea in a theory that we can do computations, in particular in 3D, Chern-Simons theory. In fact, I had tried several years ago to do this in an even simpler case of 2D topological field theories, and well, essentially they're too simple to be interesting. So it's kind of pleasant that this gives us an interesting playground. Okay, so we're sort of just exploring what this relationship between the two notions of entanglement are. Okay, very good. So we're continuing to explore, right? We're just pushing in various directions, exploring multipartite entanglement in these setups. Okay. Another sort of enticing idea here is that maybe these different fields that we're linking together here, we're entangling. Yeah, must be a whole bunch of jokes there. Maybe you can use them in fruitful ways. Right? So maybe you can use quantum information theory to do something useful in knot theory, okay, or vice versa. So, for example, and I'm just beginning to explore these connections. I'm not an expert in anything, in any of these things, of course, but for example, in knot theory, there are infinite classes of non-trivial links that are not distinguished by their Jones polynomial. Okay, so that's related to the colored link invariant in MSU2 theory. Okay, and so you can imagine that there are entanglement invariants, concepts from quantum information theory that you might use that are a more refined notion of an invariant that you could use. And we've sort of seen an example of that, right? I brought in this relative entropy in order to see more details. Okay. And there are various conjectures that people have made over the years in knot theory, for example, that you might hope to learn something about and might prove or at least understand better by thinking about entanglement. Okay, and an example of that is the so-called volume conjecture, which I'll get to in a moment. Okay, since this is a string theory crowd, I think it's natural to ask, can these sorts of things be useful in 3D gravity? Okay, so in other words, I have in mind here talking about a Chern-Simons theory that's related to 3D quantum gravity in some way. Okay, so that might be SL2R times SL2R, or it might be SL2C. Okay, and so one of the things that we're trying to do is to extend this to SL2C. And you might hope, so I'm not saying that this is holographic or anything like that. I'm not presupposing anything. Okay? There's a big stumbling block here though, which is that SL2C is non-compact. Right? And all of this nice stuff that I've been using, in particular the fact that I had finite dimensional Hilbert spaces, goes out the window. Right? The Hilbert spaces become infinite dimensional, and so you have to be extremely careful and conservative about what you conclude in that case. Okay. But you might hope to find some geometric interpretation for this multi-boundary entanglement, and you might hope that it will connect to Bekenstein-Hawking or Ryutakanogi in some way. Okay, and so we're exploring that. Okay, and I mentioned the volume conjecture. So what happens in this case is that in the case of SL2C, many link states, okay, are hyperbolic. Okay, what that means is that in the translation into metric variables from the Chern-Simons to the metric or gravitational variables, these ones emit a hyperbolic metric on the link complement. And in that context, there's a volume conjecture that talks about how the Jones polynomial, how one of these link invariants grows as you go to the semi-classical limit of large K. Okay. So again, I think we're playing around with this, but the hope is that you can make some contact with those sorts of ideas. Okay. In string theory, this is related to the so-called 3D correspondence and all of that. So this is a massive, complicated field that I know very little about, but we'll know a lot about very soon. Okay, so that's it.
Any questions?
I was wondering if people who do quantum gravity might be interested in what you were saying, because they try to make their whole space-time out of being fluid like this, and I presume they need to get the local entanglement you can see in space-time anyway for a fluid theory.
Yeah, I haven't actually talked to anybody in that field about this. I mean, so they typically work in either 3D or 4D. They would like to work in 4D, right, of course.
But the loops, I think, are only in 3D, because that's a spatial band, right? You can't really link loops to make a weave in 4D.
Right.
So it's just a 3D
Yeah.
simple manifold. Yeah, gravity would diverge out of that.
Well, I'll be at Perimeter next week, so maybe I'll confirm.
Have an elementary, yeah. Oh,
Well,
okay, that's right.
okay.
Now I can choose myself. So. I said it's a very trivial question, you probably explain, but so in the usual field theory, you take a spatial section and you compute the entropy in the Hilbert space at fixed time.
Yeah.
But here you are taking space-time being Euclidean, and you
It's
don't have it.
Euclidean, yeah.
So it's a bit different from the usual.
No, it's actually not different, because the usual construction that you just referred to is actually in Euclidean time.
No, but I mean, you
you-
compute the entropy at fixed time. You don't need all the space-time.
Well, if you want to do it sort of systematically, as I said, what you're doing is you're doing the path integral over the space-time, say for Euclidean time less than 0, with some fixed spatial
The
hypersurface.
fixed time is required to get a wave function, so now you got a wave function, so once you have a wave function,
Yeah, but you
an
have
entanglement.
the wave function evolves in time, and here with the wave function, this Hilbert space, there is no Hamiltonian or something.
Yeah,
So
I'm not
you
talking
don't,
about
you
timing.
don't need a time slicing, a foliation of the space. All you need is as an integral, a path integral over manifold with boundaries. And then you have, the answer depends on
No, I
the
understand
values
that's
and
very
boundaries.
interesting. No,
So
but I'm
because
saying usually you have some state in the, at a fixed time, I define some state and I compute the entanglement of that state.
Yeah,
And that's the entanglement. But this you are putting some space-time with boundaries. Okay.
But
No,
that's
but-
used to define the Hilbert space, the set of states,
right.
right?
The point is, to get the state, you have to do the path interval, the same path interval.
Okay.
So this is like, sort of morally, this is like state as in gravity, like, with a equation which give a state which we sometimes construct like this. So I think there of the time is a funny thing.
Well, I mean, you don't need gravity, it's just it is the concept of a wave functional in field theory.
Yeah, but the fact that you have a sort of a no boundary, like the fact that you do a wave function in a Euclidean capped off thing, sort of connects to.
Yeah, but it's not but, it's not necessarily gravity.
No.
It's
I
not
didn't
the
mean
vacuum,
gravity,
there
but
are, there are many states.
similar in that.
I thought it was different because it was a gauge theory, but you're saying it's the same, so you don't need any.
So you've done it for U1 and SU2. Is it clear that you'd get even qualitatively similar results if you did, say, SU3? That the things that you were seeing were like W-like, or I forgot the initials, GHC-like, might,
Maybe.
it's not clear that if you did it for a different gauge group,
It's not clear, it's just harder. I mean, there are other examples that, condensed matter people might be interested in.
Mhm.
Right? Like there are these so-called regularized states, which are, I actually forget the names. Is it regularized? Anyway, more read. There's things like SU2 times U1 mod U1. And this is something that's realized in
Mhm.
quantum Hall states, for example. So, you can imagine doing cases like that. You can imagine doing SUN.
mhm.
But yeah, I have no idea whether there's going to be some qualitatively new information or not. It's interesting.
And from the knot theory point of view, the knot invariance that you get by doing SUN, do they? I don't know. I'm just ignorant of the ones that you get, these colored knot invariants or whatever they're called from SU2. Are those equivalent to the Jones polynomial, or are those more refined? And then
Yes, yeah. So the coloring here refers to a choice of representation of
Right,
SU2.
right.
But I think people have. I mean, I'm not an expert on this either.
Uh-huh.
I don't really know what's out there, but there are certainly lots of results on, say, SUN non-invariants. But I think they're less well understood.
But they do in some sense give the larger and more refined invariants that capture, or you don't know.
So you have this formula for the entanglement entropy with the greatest common denominator. So if you were to imagine trying to connect this with Hawking, you would expect the entanglement entropy of some black hole, I guess, to have these number theoretic properties where they jump all of a sudden at particular values of the Weinstein number.
Maybe.
Any thoughts?
As I said, the Hilbert space isn't discrete anymore.
Uh-huh.
Right? They're sort of depends on how you think about it. They're sort of a Heisenberg continuous. There's sort of an L2 thingy tensored in, and as I said, because it's because it's now an infinite dimensional Hilbert space, you have to be pretty careful about defining things. So I just don't. At this point, I don't know. I can't really say anything definite.
So about the large K limit and also the relation to the geometry, do you really need to go to SL2? Can we learn something even for SU2? Just staying in SU2 and study large K?
Yeah, you can do that. In fact, that was the original cachet of conjecture, because part of the part of the you have Q, right, which is sort of, and part of the conjecture was to take that to a particular K plus 2 unity. So that was the connection to the Jones polynomial and the SU2 in particular. That's a pretty subtle. I mean, we played around with it a little bit, and it's pretty subtle. It's more subtle than you might have expected. But yeah, but then the generalizations.
Okay, so thank you. So the next talk we start then 11:30. So we have some break, and you can ask more questions during the break, I guess, or some discussions. The thing is that the next two talks will be Blackboard talks, and we have to be facing that way.